Today we are discussing about the law of thermodynamics. In this chapter there are many topics included. The first law of thermodynamics, thermodynamic process and the first law, human metabolism and the first law, second law of thermodynamics, heat engine, refrigerators, air conditioners and heat pumps, entropy and second law of thermodynamics, order to disorder, unavailability of energy, heat death, statistical interpretation of energy and the second law, thermal pollution, global warming and energy resources. All these topics are based on the thermodynamic process. Then we discuss about the first law of thermodynamics. The change in internal energy of a closed system will be equal to the energy added to the system minus the work done of the system on its surrounding. The reaction becomes delta U is equal to Q minus W. Delta U is change in the internal energy, Q is the related to heat and W is the related to work done. This is the law of conservation of energy written in a form useful to systems involving heat transfer. Then we discuss about the thermodynamic process and the first law. Thermodynamic process in which isothermal process is considered. Isothermal process is the one where the temperature does not change. Its mean temperature remain constant. The process is known as isothermal process. In order for an isothermal process to take place, we assume the system is in contact with the heat reservoir. In general, we assume that the system remains in equilibrium throughout all the process. Thermodynamic process and the first law. An adiabatic process is one where there is no heat flow into or out of the system. This is the graph between pressure and volume, and isothermal and adiabatic. Isothermal where is temperature is constant, in adiabatic heat is remain constant. An isobaric process in first graph occur at constant pressure, there is no change in pressure, and isovolumetric one at constant volume. B represent the isovolumetric curve in which volume remains constant. Thermodynamic process and first law. If the pressure is constant, the work done is the pressure multiplied by change in volume. We can say that at constant pressure, work done W is equal to P delta V. Delta V represents here change in volume. In an isometric process, the volume does not change, so work done is 0. In isometric process, there is delta V is equal to 0, so W is equal to 0. Thermodynamic process. For process where the pressure vary, the work done is area under the pressure volume curve. This is the pressure volume curve where work done is represented by the lines. And there are different processes: isothermal, isobaric, isovolumetric, adiabatic. Isothermal where temperature remains constant, isobaric where pressure remains constant, isovolumetric where volume constant, adiabatic where change in heat is equal to constant या 0. According on the basis of this process, we can calculate the first law of thermodynamics, that is the delta U is equal to Q minus W. Human metabolism is also based on the thermodynamics process. If we apply the first law of thermodynamics to the human body, we know that the body can do work. If the internal energy is not to drop, there must be energy coming in. It is not in the form of heat. The body loses heat rather than absorbing it. Rather, it is the chemical potential energy stored in foods. The metabolic rate is the rate at which internal energy is transferred in the body. Second law of thermodynamics. The absence of process illustrated above indicates that conservation of energy is not the whole story. If it were, moves run backwards would look perfectly normal to us. The second law of thermodynamics is a statement about which process occur and which do not. There are many ways to state the second law. Here is one. Heat can flow spontaneously from a hot object to a cold object. It will not flow spontaneously from a cold object to a hot object. Heat engine. It is easy to produce thermal energy using work, but how does one produce work using thermal energy? This is a heat engine. Mechanical energy can be obtained from thermal energy only when heat can flow from a higher temperature to a lower temperature. And this is the diagrammatically representation of second law of thermodynamics, where lower temperature represented by TL, higher temperature represented by TH. Here heat flow from higher temperature to low temperature. Heat engine. We will discuss only engines that run in a repeating cycle. The change in internal energy of a cycle is zero as the system returns to its initial state. The high temperature reservoir transforms an amount of heat QH to engine, where part of it is transferred into work W and the rest QL is adjusted to the lower temperature reservoir. Note that all three of these quantities are positive. A system engine is one type of heat engine. The internal combustion engine is a type of heat engine as well. Heat engine. Why does a heat engine need a temperature difference? Otherwise, the work done on the system in one part of the cycle will be equal to the work done by the system in another part, and the net work will be zero. Heat engine. The efficiency of heat engine is the ratio of the work done to the heat output. A is equal to W upon QH. Using conservation of energy to eliminate W or find. This is the efficiency of heat engine. E is equal to 1 minus QL upon QH. QL is the lower and H is related to high heat. Heat engine. Carnot's engine was created to examine the efficiency of heat engine. It is idealized as it has no friction. Each leg of its cycle is reversible. The Carnot cycle consists of 4 parts, that is isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Next we will discuss in next video.